Kate. I'm a civil engineering major here at UNF. So this is a project that we're currently working on. One of the requirements in this class is that we build a tower with actually an elevator that we would use a 3D printer to build the cart of the elevator. So as you can see, we use popsicle sticks as well as regular Elmer's glue, excuse me. And another thing that we're working on is this little metal tunnel that we have. Our plan is to put a marble at the top and have it swivel, make its way down here, and it's gonna hit a car, and we hope that it will work. Now, the great thing about this class is that our students are exposed to all three disciplines that we offer here at UNF. So that is civil, electrical, and mechanical. So as you can see, we have wires as well as batteries where our students are able to work in that field. We have the structural aspect for our civil engineers and as well as gears and stuff like that for our mechanical engineers. So actually, when I came to UNF, I was a mechanical engineering major because I loved working with cars and looking at them. However, when I took this class and I was looking at the civil aspect of it, I realized that this is more interesting than mechanical. So if you are interested in engineering here, no worries, because this Intro to Engineering course is required for all engineers.
What's up, it's Jordan. I'd say Introduction to Engineering is definitely one of the most helpful classes that I've taken here at UNF, just because it gave me a real hands-on experience, and it really allowed me to get my hands dirty and just collaborate with other team members. We did a project that was similar to this one where we had to incorporate pulleys, and we had to also have a structure like they have here. The structures are all it incorporates civil and mechanical right here.
Well, my favorite thing about Intro to Engineering was how integrative it was and collaborative, because each individual group not only works with civil, mechanical, and electrical engineers, but you have your own individual goals, as well as there's a goal of the entire project where you have to work with other teams and not just amongst your four. So even though it's a group of four, it's really a group of 120 possible students at different times. So it's really practical in that way, just like in actual industry.
Hello, I'm Dr. Jadan and I'm the director of the School of Engineering. My undergraduate was in civil engineering, my PhD was in mechanical engineering, so a little bit of everything here. We are in the Mechanics of Materials lab, and this is a course that's taken by civils and mechanicals. And the course in general is about how to characterize the strength of materials. So if you want to build a bridge or a building or a machine, anything that sustains loading, you want to make sure that when you design it, you know the strength of that material, what makes the material breaks, and how you design against failure. So this is a very nice piece of equipment, brand new. We just got it last year. And we call it it's a tensile testing machine, but it also does compression, it does fatigue testing, cyclic loading. And what we do is we basically take a specimen of a material. So this is a specimen of steel. It can be aluminum, copper, cast iron, plastic, whatever you want it. And we mount it here between these two grips. And basically the machine pulls at the specimen until it breaks. And while the machine is pulling at the specimen until it breaks, the data acquisition system is collecting the data on this computer, and it's measuring how much load it takes to stretch the material a given amount, and that gives us what we call the rigidity of the material, the strength of the material, what it takes to break it, and we characterize all sorts of materials so we can design against failure. This is a heavy piece of machine. It can test north of 100,000 pounds. It's a Shimatsu 600 kilonewtons machine, so 120, 125,000 pounds in that order of magnitude. So this is one of the experiments that our students do to learn about material properties.
Hey everyone, my name is Dr. Ryan Shamit and I'm an assistant professor here with the School of Engineering, specifically civil engineering and boiling it down even a little bit further, geotechnical engineering. So my passion for geotechnical engineering started back when I was a kid, collecting rocks and just playing outside and seeing how structures and bridges and other types of these elements that we use every day, seeing how they interact with the ground and the groundwater, and seeing how we can build on top of these to create bigger and taller and safer structures. Where we are today is the Geotechnical Engineering Lab, and this will be, you'll use this lab for several of your core courses, specifically Geotech and Foundations. And in this lab we get to work with soil, and we get to test different types of soil in different types of capacities, simulating real-world conditions and seeing at what loading rate and at what different type of criteria our soil will fail, and which will greatly affect the structural design, which you'll also be learning about. So behind me we have a few of the testing apparatuses that we like to use. This one's really interesting because we can recreate the ground conditions. We take soil samples, we remold them, and then apply different confining pressures and different overburden pressures to simulate a soil condition that may be 30 or 40 feet underground. So this is really important because now we can test it until failure and recreate again that loading conditions that we may see from a bridge or a skyscraper or whatever type of structural design that we have. So you could probably tell by the name Geotechnical Engineering, but it's kind of a combination of geology and then engineering. So one of the things that you'll get exposed to in this lab is various geological conditions and various types of resulting soils and gravels throughout the state and throughout the nation. So as geotechnical engineers, a design up in Gainesville is going to be completely different than a design over on the West Coast in Tampa. Likewise, on a regional scale, even east side of Jacksonville is going to be completely different than the west side over by the St. Johns River. So in this lab, we get various soil samples from throughout the city of Jacksonville and throughout the state, and we do different types of tests to see the different engineering parameters, which again affect the overall design and the capacity of what we can put on that land structural-wise. Okay, so another interesting piece of equipment I have right here behind me is called a permeameter. So in this lab, we also look at the interaction between groundwater and the different types of soil conditions. So this is really important. You can probably tell in Florida, where we have these massive rains and lots of flooding, and we need to see how quickly the groundwater or the surface water will flow through the soil. So this is an important test where we get to actually recreate those conditions in the lab. We can put different hydraulic levels and determine the flow rate or the drainage rate of those soils in various types of hydrogeological conditions. So not only is it important to determine how water flows through the different types of soils, but it's also important to know how much water absorbs in other types of soils as well. If you go in one region, you have a clay versus a gravel, obviously they're going to drain water differently, but they will also absorb and swell and shrink as we change the moisture content as well. So in this lab, we also have different techniques to measure the mass-volume relationships in its dry and in its saturated conditions. And of course, these are important to recreate different types of flooding scenarios or drought scenarios in the real world. We also have a load testing cell here where we can test how the moisture content affects the strength of the soil conditions or the gravel conditions. So these are just a few more examples of some lab techniques that are again used to recreate the field conditions here in a more controlled environment in the lab. All right, welcome to the Civil Engineering Materials Lab. So this lab's a little different than the Geotech Lab, where we start looking more at the production of common construction materials, such as concrete and other types of asphalts and other aggregate mixes. So one of my favorite things to do in this lab is we get to make concrete and we get to break concrete and test its compressive strength. So to do that, we use this machine here. This is a loading ram capable of loading concrete up to 10,000 PSI. So it's a hydraulic press, and it shows the loading or the resulting load at this little readout here, and we get to make concrete samples using different types of mix designs. So you'll learn about how the water and the cement and the aggregate affects the strength. And then of course we put them in this machine and we load it until it fails, and we get to determine the compressive strength, which is really important for design and really important for quality control when you think about all these bridges and and roadways that are made out of the concrete. We want to make sure that the concrete is high quality, so we take samples here in the lab, break them, make sure they meet our criteria. So aside from utilizing this space for a coursework and a concrete capacity, we also will have the opportunity to use this space in a research capacity. So you'll have lots of opportunities to study various more advanced topics and work with real-world practitioners and on real-world grants to solve everyday's engineering problems. So one of those research opportunities consists of looking at the chemistry of cement and concrete. The different types of aggregates will have different chemical reactions, and different types of cement paste will have different chemical reactions and different chemical constituents that are important to study and learn about the interactions so we can build a more environmentally friendly and a more sustainable concrete and cement mixture design.
Hi, my name's Raf Crowley. I'm an associate professor in civil and coastal engineering here at UNF. And I'm here today to talk to you about some of the things that we're doing in the coastal engineering program in this lab here. What you see is a bunch of big equipment, and kind of we'll talk about some of the work we do with it down here. So what you see in front of you here, this is known as the sediment erosion rate flume. Shorthand is the SERF device. This is an instrument that the Florida Department of Transportation has put about 20 years into developing. I started developing this when I was a grad student down at UF and brought it up here with me to UNF when I came up here in 2013. What it is a giant system to measure sediment's erodibility. So the way this works is goes in a big loop, and you have water that comes out of this big tank that you see over there, through a couple of pumps that are probably off camera at the moment, and then through this rectangular duct, back out through a filter, and then back into the tank. As you can see from the PVC that we have on the floor, we're currently in the process of finishing setting this up. What makes the system unique is that it's automated, which means what we can do is we take a tube that looks like this, and then we get a sample of soil from the ground, and we extract it with this big looking thing over here. This is known as a Shelby tube extractor. And so this sits on the end over here. We push a tube of soil into this tube of soil, and the reason we have to do that is because the tubes of soil that you take out of the ground usually aren't round and they don't seal that well in the device. Once we have a tube, we stick it up into this device like this, just so that the sediment sits right at the bottom of the flume. Then what we do is we flow water over it, and as we're flowing water over it, it will erode. As it erodes, we push it up using this stepper motor right here, so that it's always level with the bottom of the flume. To control advancement, what makes this device unique, again, is that it's automated. So we have on the top here an ultrasonic depth array, and on the sides here we have a little laser/photoelectric sensor system. And the idea with the laser photoelectric sensor system is it kind of works like a garage door opener, in the sense that if the sediment is blocking the sensor, then it means it doesn't need to advance. If it's not blocking the system or the sensor, then it means that it does need to advance. So with these two systems, we can control advancement, which makes this whole process automated and allows us to run an erosion test. The reason these are important is because erosion and scour around bridges is the leading cause of bridge failure in the world and in the United States. This problem costs us $50 million per year. I just looked at the updated scour list from the Florida Department of Transportation the other day. In the state of Florida, we have 100 bridges that are scour critical. So this is a big problem. When we test erodibility, what we're doing is designing better for erosion and scour. That's one of the things we look at in coastal engineering, is improving bridges like that. Some other things that we're working on over here include this kind of ugly looking sandbox here. What this is it started out as just beach sand that we took from Atlantic Beach. And then what we did is we added bacteria to the sand. This is naturally occurring harmless bacteria that you find in all sorts of soil. We just added more. And then we fed it with sustainable ingredients, urea and calcium chloride. And what you end up with is this, which is a crusted surface that sticks together. And so what we can do is we can use this, hopefully, this technology on the beaches and the intercoastal marshlands and things like that to give us sustainable erosion resistance that doesn't involve having to do things like build a seawall or put in riprap or things like that. So this is another ongoing area that we have here. Last thing I'll talk about is this funny looking thing over here. Kind of looks like a sailboat. It's not. What it is a buoy system to measure underwater noise due to pile driving. So when you build a bridge, you drive a number of piles. That makes a lot of noise that could harm marine organisms and wildlife. What this does is right here on this mess of wires that we get on top of the box here, we have two things. We have a temperature probe and a hydrophone. And the hydrophone, when we have these things deployed, comes off the back of this thing, and it reads what the noise level is at a construction site. If we open up the box, what you'll see is a couple of batteries and a data collector would sit right about here, one for the temperature and one for the noise. And then this is just a power adapter. The reason we need power is for this antenna thing here. So it looks like a giant antenna, it looks kind of like a sailboat. The reason it's got the antenna sticking out of it is because the data from the hydrophone is sent back to those of us on the field crew on a boat in real time through this antenna via this Wi-Fi network that with this really big antenna we can get about a quarter mile of range on this thing. And so what this allows us to do is collect the data, look at the data as it's being collected, make sure there's no anomalous readings, things like that. We have 4 other buoys like this for a total of 5. About half a dozen sites around the state of Florida over the past couple of years. So if you see us at a bridge site and you see these funny looking sailboats in the water while there's construction going on, that's us for measuring underwater pile driving noise. Hopefully you are interested in civil and coastal engineering, and look forward to seeing you in class in the next couple of years. Thanks.
Dr. Alan Harris, I'm an Associate Professor of Electrical Engineering, and I'm giving you a tour of one of the lab stations in one of our 3 main electrical engineering teaching labs. So in the electrical engineering curriculum, you'll go through multiple classes that take labs in one of these rooms, and just wanted to kind of give you an idea of what they look like and what the equipment is in here. So in one of these labs, each station is set up exactly the same, and normally you'd work in teams of 2. Obviously right now we're working in teams of 1, and we have some nice plexiglass in here to make sure everyone's protected. Each station in here has the same set of equipment. So there's a cadet breadboard prototyping station. So this is a station that lets you prototype different electrical circuits. And we have some labs that do analog circuits, some labs that do digital circuits. And then each station has a mixed signal digital oscilloscope. So this is going to be the device that lets you connect to your circuits and look what's going on, look at what the voltage and things looks like inside the circuit. And then each station has a benchtop multimeter that lets you take some different measurements as you're going through your classes. We have a DC triple output power supply, and then we have a function generator. So all of these, each station is a little self-contained station that lets you go through the semester performing a series of experiments, getting that really good hands-on experience, building different circuits, learning how they work, learning how to troubleshoot them, and getting your legs as an electrical engineering student.
Hello, this is Dr. Juan Aceros. I am a professor in the electrical engineering program here at UNF. I want to today welcome you to my lab. This is the Adaptive Toy Project Lab here at UNF. And what I want to show you today is a couple of projects that we have within the program. They are all biomedical engineering projects. And then we're going to talk probably 90% about the Adaptive Toy project, which is the core of the lab. So to start with, I want to show you a few of the projects that we work on. For example, a speech therapy toy. This is a speech therapy toy that was developed with Wolfson's Children's Hospital, where a child may be able to engage with the toy while speaking. So he will pronounce words, and then the toy will react when the child pronounces those specific words. Over here we have also a Bowie machine. This is a project with Mayo Clinic, where we're developing what we call artificial tissue, which is tissue that can be used for surgical training. So this machine, it has an RF knife, which means that it has electricity, and it will cut, it will burn, it will coagulate. And so this is what they use in surgery at Mayo and many other hospitals. And what happens is that there's not a lot of artificial tissue that can be used for training. So what we're doing is that this tissue is electrically conductive, so that when the knife goes into it, it will behave like a skin, for example, in a human patient. So they can use these type of materials for training. We also have here what we call a smart walker. This smart walker has embedded electronics. Okay, so we are using Arduino as well as some amplifiers, and it has sensors on the handles of the walkers. So what we do here is that we test posterior and anterior walkers, and we try to look at the efficiency of these walkers. This is something that's used for rehab, and is also used for research on gait, and to study how people are loading the walkers, and when are the people who came out of surgery, for example, are they improving over a period of time of therapy. So let me now talk about the adaptive toy project, which is what we see right here, this Jeep. This is a ride-on toy. And this ride-on toy is commercially purchased, and what we do is that we modify it. And we modify it so that children in the community can actually employ it. Here, for example, we have a picture of a child. This is something that you're going to see outside on our hallway in the School of Engineering. This is a child that received one of these toys, and you can see that he's actuating the toy, and this specific toy follows a black tape on the floor. The child has a visual impairment, so he's unable to control the direction of the toy, but he's able to control when the toy comes on and off. Okay? And so what we do with these ride-ons is that we modify them. We normally will open the inside of the toy, and we will basically look at the guts. We will put some electronics into it. We will modify the motor control, so we will have a motor controller. We typically use a saber tooth. And sometimes we use also an Arduino if we have other sensors. For example, when we have lights and we may have sound, we may have other sorts of feedback, or sometimes we have pressure sensors on the car. Okay, and then we have a proportional control joystick, which is placed right here in the middle. Sometimes we place it on the sides also, and sometimes we use this in a wireless mode, where the child can actually put it wherever they want. And what they do is that they will control the car using this joystick. It makes it a lot easier for them to control the direction where they're going, as well as the speed. We can program the speed and acceleration of the car. We modify, we provide postural control. A lot of these children have conditions that basically they present a weak neck, a weak trunk. They have weakness in the hands also, and they're unable to extend their arms, for example. So they have mobility impairments. Most of them are unable to walk, and that's why using these ride-on toys is very important for them, because it provides them mobility. They're able to play with other children, they're able to go from point A to point B, they're able to engage in daily activities, and that's what we want. We want them to be able to play with our children, because at that early age, play is the way that they acquire skills, that's the way that they learn. They are engaging in play, they are learning communication, they are learning social skills, they are learning everything that we take for granted, okay? So it's extremely important for them to be able to engage in this. So we provide all of these frame, we have a 4-point harness, 5-point harness, and all of this is basically to be able to provide safety for them, so that the car is safe, as well as useful for them at their home. So this is basically a rehab toy that they can use while they're remotely at their home, playing with their friends, with their brothers, with the siblings, and so on. So we have done quite a bit of research on this, and we have shown that mobility at early age, when there's a very quick neural development, has a strong impact on the children. We have actually proven that children should be recommended to move at that early age, between 6 months and 5 years old. We have published those papers. We have a lot of students that have come in. They have done the work, done the research, gone to conferences. These are undergrad students as well as grad students, but a lot of undergrad students who have flown through across the US to different conferences and presented their research. And they are now gone to either grad school or have jobs at companies coming out of working in this type of project. And so I encourage you guys, if you're interested in biomedical engineering, if you're interested in working on any of these type of projects that involve electrical or mechanical type of work, to just approach me and we can start getting you trained. The sooner you get trained on the projects, the more productive you're going to be later on in your junior and senior years. Thank you very much.
Welcome to your Engineering Fabrication Lab. I'm the instructor, Steve Andropont, and the reason I say your lab is this lab is intended for you to come in, get your hands dirty, and put your hands on all these machinery to be able to build parts throughout your learning career here at UNF. This isn't a shop where you bring parts in for us to cut for you. You're going to come in and you're going to build them with your own hands. With equipment like this, a manual milling machine. We have manual lathes. We have a full suite of woodworking equipment, sheet metal, computer controlled and hand tools for all applications that you may need during your time here. So in addition to the manual mill that you saw earlier, this is our manual lathe. This machine will turn round parts, like this one, where the manual mill would machine away parts and blocks like this. So this would be, possibly one of your student projects that you would build. We want you to be able to get your hands on a machine so that when you are designing something out there in the world, you've got some idea of what it takes for a machine shop or a subcontractor to build the item that you're designing. So by you having time on the machine, it makes you a better designer. This particular piece of equipment is a sheet metal shear for cutting large sheets of sheet metal, and it will go along with our bending tool for forming sheet metal. We have a variety of saws in the shop. This one in particular is a horizontal band saw that would be used for metal items as well as wood. So in the other room you saw all of the manual working equipment, mills and lathes. Well, in this room we have all computer controlled tools. What would take 10 or 15 minutes to produce a part on the manual machine, these machines behind me may produce them in 30 seconds to a minute. One of many 3D printers available to the students is here in the lab. And finally, CNC water jet. So, examples like this where precision cutouts of sheet metal, glass, stone, elastomers can be cut with very high pressure, very high speed water. So this is just some of the tools available to you here in the Engineering Fabrication Lab during your time here at UNF.
Hello, I'm Steve Stegon, Associate Professor of Mechanical Engineering and also the Program Coordinator for the new Advanced Manufacturing program that we're launching here in fall 2021. What I work on is a lot of diverse research in the area of nanotechnology and surfaces. So I have several grad students in my lab, and every semester I have several undergraduate students in my lab, and the students are all doing experiments. So we do hands-on experiments, and we actually take things we fabricate here and we use them for different applications. One of our biggest applications is actually using nanostructured surfaces we grow in this machine right here, the physical vapor deposition machine, to detect trace amounts of substances. And right now we're in the middle of this COVID-19 pandemic. We're all trying to do what we can based on our expertise to help out. One of the things that we're really passionate about is using these nanostructured substrates along with a method called surface-enhanced Raman spectroscopy to try to develop a new platform for the rapid and low-cost detection of the SARS-CoV-2 virus from different people's biological samples. So we're working with several universities on that, and we're trying to develop that into a real technology that can be at point of care. meaning at the doctor's office. And that's just one of the things that we work on. We work on other projects in surface coatings for 3D printing. So we try to take a plastic 3D printed part, and we try to take and turn that into something that's actually structural. We turn it into something that's functional and put different metallic and organic layers on the exterior. So that's what we work at in this lab. This is the heart of the lab right here. This machine is actually a large high vacuum chamber. In this chamber, we take all of the air out, or most of the air. We get it down to less than 1/1000th of an atmosphere. So essentially there's very few air molecules in there. And we're actually able to vaporize metal so that we can plate a variety of things. If we vaporize it in just the right way, we can make surfaces that look like this that have unique surface properties. So for example, this is a microstructured surface, and we're able to make these kinds of things right here in the chamber. Over the last 7 years, I've had more than 40 undergraduate students work in my lab, and we've graduated now 4 graduate students with a master's degree in mechanical engineering. So with that, we're actually starting a few new things that I think are of interest. The bachelor's degree in advanced manufacturing will be launching in 2021, and it's going to be the most cross-trained degree. So we're actually taking in topics from mechanical engineering, electrical engineering, material science and engineering, and industrial engineering, bringing it all together to make a really cross-trained, hireable engineering graduate student or engineering student. And then we're also launching the new master's degree in material science and engineering, also coming fall 2021. And that's a really diverse program with people from things like materials, mechanical engineering, electrical engineering, chemistry, physics, and biology. So you get a chance to work really cross-disciplinary. This is the kind of stuff that you get to do if you come and do research with us. And we have a lot of resources here. You've probably seen the Fab Lab already, where we have a variety of 3D printers and CNC machines. We have 3D printers in a bunch of our mechanical engineering labs. I have 3D printers, Dr. Bevel has 3D printers. We have them all up and down the floor. If you come and you work on this undergraduate research with us, you're really going to get a chance to do hands-on stuff.